Good afternoon. I have uploaded assignment 8 and the deadline is the 4th of April. So this is the beginning of the reading week. And you should be able to do all the questions now actually, except perhaps the last 2 questions. And don't forget, we have exercise classes tomorrow. Okay, so tomorrow you are going to see more partition functions. And today, in today's lecture, we are also going to play a little bit more with the partition function. And of course, this will come back again next week and after the reading week. But I'm going to also introduce something new today. Okay, so before we go ahead and learn the new stuff, let's take this chance to apply the partition functions again. So basically, this is the most important slide from last lecture. This is the stuff that we spent time to develop. Okay, so this is from last lecture. This is the recap really. We don't want to talk about all this again. But the message is here, all the central message is here, except that I probably forget the sausage machine here. So the idea is this is a summary from the last 2 lectures. And what is written in orange at the top is what we are going to learn very soon. Because we are going to finish this chapter today and we are entering the new chapter on indistinguishable particle, and there we really will have to play with the partition function again, and you discover this relationship between the partition function of the entire system and the partition function of a single particle. Okay, so as just a reminder, we are still talking about distinguishable particles at the moment, and for distinguishable particle you have 2 different ways to view the same problem. So one is to view it as n identical energy spectrums. So you have this energy spectra and they are all identical. Or you can collect all the energy, possible energies of the entire system. So this is the same system. And surely if you have the same system, you just change your way to view it, you must get the same result. And that is what we went through. Okay, so what we develop using the single particle partition function are given in the typeset black color equations, and what we develop for the equation, the corresponding equations for an assembly of particles are written in orange color. Okay, and then they are really equivalent because of the fact that you can pull this n inside the you can group together n with log, and then you raise the single partition function to the power of n. Okay, so that is not surprising. And then the last thing I want to say is, if you only want to memorize one set of equation, memorize the one in orange. Okay, because they can be applicable to the indistinguishable particle as well, as long as you define z sub n properly. Okay, and at the end of last lecture, this is another recap. We talk about this problem, so this is also recap. We already talked about this. And I told you how to evaluate the heat capacity for the problem. So this is the heat capacity for a 2-level system. We use a spin as an example of the 2-level system. So there we went through a lot of physical intuitions. I skip a lot of mathematics because I believe you can do all this, and we spent time instead on trying to understand the limiting cases. So I hope you managed to learn a lot about the system, the spin This is spin half, very simple, two-level system. You can write everything down very quickly. And we even link all the way back to the coin problem. And that allows us to discuss, to understand very well the limiting cases for the internal energy and for the entropy, and also to get some physical explanation of why the heat capacity behave like drawn up here. Okay, so this is all covered in the last lecture. And today we are going to go to the other extreme. So rather than talking about two energy levels, I'm going to talk about an infinite number of energy levels. And this is the Einstein model of heat capacity. And as claimed, now if you understood my argument on Monday, then you should be able to draw the bottom figure. Right? I told you my explanation of why the heat capacity shows a peak for the two-level system. And now imagine you keep adding more levels to this ladder. So if you have more and more thermal energy, you can always find somewhere to go. Your particle can always take advantage and go to higher and higher and higher energy. So with this argument, you should be able to already draw this shape for me. Okay, so that this one at the bottom is something that you can use the same argument to draw. Okay, so that is the bit which you should understand. But today I want to really give you this formula to show that this is correct. And I'm going to also mix in some solid state physics. And therefore, let's begin. What is the model we are talking about? And this Einstein model basically is looking at something like this. Let's say you have atoms in your solid, and you know they are bonded together, and we physicists like to draw bond like this. Okay, we link them by spring. And here there are lots of things to talk about in solid state physics. You will see this problem again if you take solid state physics, but you will see it from a different viewpoint. Okay, so here I'm going to give you what we can already get using the machinery we developed so far. Okay, so I'm going to draw a bunch of springs. It goes to infinity, and this is a 1D chain. Indeed, when you do talk about when you do solid state physics, this is your starting point. But what we should also bear in mind is we are really talking about three-dimensional solid, right? So we should at least I will draw a bit more for you. So this is the problem you should keep in mind. Okay, so this is a simple problem. You can add more complication. Now, the way I draw it seems to suggest that all solids are cubic, but that is not true because you will have all kinds of structures. Okay, so the Einstein problem is this. Einstein wants to understand the heat capacity for a collection of oscillators like this. This turns out to be a perfect map to the problem of solid state. What you can think of it is like this. All this bonding will give you the problem of harmonic oscillator. So if you solve this properly, you will find the solution is a solution of harmonic oscillator. And each atom is, these atoms are identical. They are distinguishable because now I talk about solid. Solid means all these atoms are localized. You know the address. So this is a perfect problem for us. It's a perfect problem that we have the perfect tool to solve. Okay, so for each atom, if you single out one atom, you know the energy spectrum from quantum mechanics. So the energy spectrum will be some kind of quantum number plus a half. Now, unfortunately, I run out of notation. This is n, but not to be confused with the number of particles. This is really the quantum number characterizing your energy spectrum. And the energy spectrum is a famous form like this. Okay, so you have n plus a half times h bar omega, where omega is the angular frequency, which characterizing the oscillator strength. So we have a lot of oscillators. harmonic oscillators. And what is the strength of this oscillator is characterized by your omega. Okay, and this n start from 0. So when you are at 0, you get your 0 point energy, and then the energy is exactly like this picture I drew earlier. You have a ladder of energy levels, and they are equally spaced. Okay, so this is one of them. This is what will go into your single particle energy spectrum. But you have n particles, they are identical. Okay, so this is all simple harmonic oscillator are identical. So you have a bunch of energies like this to deal with. Okay, so they are identical with the same angular frequency. Omega. So this is of course the simplest approximation. Don't get the wrong message that this is a full solution. Einstein managed to fit the data very well, but he was not the only one who came to analyze the heat capacity of solid. And in fact, when you go to low temperature, this approximation, this model also doesn't work quite well. That will bring us to something else, which is called a Debye model, and we will also have time to deal with this. Okay, so let's begin with Einstein. So let me write a little bit more about this. This n is the quantum number characterizing the problem. Okay, and you must not get confused. This is not the particle number. It's not the particle number we used to use. Okay, this is a 3D problem, but it's very symmetric. So I will start from the 1D case, and once we understand the 1D case, we'll be able to very quickly write down the solution for the 3-dimensional case. So 1D case means I'm going to look at only one chain, such that this atom can only vibrate along one of the directions. Okay, so that is so if we start from 1D, and we will see what happened. Okay, from 1D, we can write down the partition function for 1D. So this can, for example, be this chain here along the x-axis. But I will label 1D, and you should hopefully be able to recognize that the x, y, z direction are the same. They are all the same as this form. Okay, so let's see what happened. For the partition function, you don't have much to do, right? You just really write down e to the minus energy divided by kBT. You just do that. And this energy has to include everybody. So you start from the lowest energy value, which is a half h bar omega. Done. This is the first term. Then you move on to the second term, and you have a half. This one is not that. Sorry, where am I? So you have the 0 point energy plus n equals 1. So you have h bar omega. The whole thing divided by kBT. And so on. Okay, so this is very different from spin 1/2, the 2-level system. You only have 2 terms, but here you have infinite number of them. Okay, and then you realize everybody has this 0 point energy, so you can pull out this factor. So that is e to the minus a half h bar omega. So I'm going to bring this a half. I'm going to write it like this. Okay, so you pull it out. The first term is 1, and the second term you are left with e to the minus h bar omega on kBT. And the next term you have is e to the minus 2 h bar omega divided by kBt, and so on. Okay. Now here you should now you need to think about how to continue. What do we do next? The thing to see is what is inside this square bracket. It's a geometric series. So this is a geometric progression, geometric series, which you know how to sum. So this is a geometric progression or geometric series. For the stuff inside the square bracket. So okay, this one. Okay, this is a geometric series. So this is like 1 plus r squared plus r cubed plus r whatever. Infinite number of them. And you know the result. And the result is this. You have 1 over 1 minus r. And this is e to the minus h bar omega kBt. Okay. Okay. Now we live in now later. My goal is I want to develop this the expression for heat capacity. More importantly, I also want to be able to compare with experiments. So I need something more realistic. Now, if you want to do experiment on a 1D chain, it's very difficult. First, if you are doing this kind of study, you know, you need a lot of material. You want to measure heat capacity accurately. You want a mass. The mass of the material has to be large enough. So it's very difficult to isolate out, let's say, a chain. And then you do heat capacity. That is a very sophisticated measurement. So I would like to take one step back and really look at the case when we have an isotropic bulk material. Okay, so what can we do? So now let's write down the energy spectrum for the three-dimensional case. So if I have a three-dimensional spectrum, my energy spectrum will be governed by Nx, Ny, and Nz. Okay, in the sense that the oscillator can take independent value of Nx, Ny, and Nz. Okay, and they can do it independently. So I will have oscillator along all different directions. So the energy has to be the sum of this. Sorry, Nz. Okay, such that these ends are really independent. So I can have 0, 0, 0. I can have 1, 0, 0. I can have 0, 1, 0. I have all kind of combination, but each one of them can start from 0. So there is, of course, the constraint. They cannot go minus. They must be integer, and they can start from 0. And the values are independent. So the value of Nz doesn't affect the value of Nx and Ny, and so on. Okay, this independent is very important. Okay, so in this case, now what is the partition function in 3D? If I now assume this energy spectrum. Okay, so in the past, for the foremost slide, for this slide, this is really for the 1D case. All right, so I write this down, and now I write down something longer for the three-dimensional case. And my question is, what is this single particle partition function? Now I think I don't want the chat now. So I will tell you the answer. You see, when you write the partition function, you write e to the minus beta times energy, right? So that is to say, if you put this energy, this form of energy, you can see there are three terms that are summed together. That is to say, you can independently evaluate the partition function for the x direction, right? So that gives you the first partition function, ESP1D. And then you have the one for the y, but because of this sum and the whole thing enters an exponential function, this becomes a product. So I'm going to have I'm going to put x, y, z for you. So this is the partition function for x. Then you have a spy here, and then you have this. And for the way I set up the problem, it's not difficult to understand that they are the same. Each one of them is this. And you have three of them. So this is the result. And that is why all the effort we put in for the one-dimensional case is it's not wasted. Okay. And done, actually. This is the first step. Right? The first step of a very general recipe. You have seen it already. You start from partition function and then you move on. Okay, the next thing, of course, is I want you internal energy. And I want the internal energy in 3D. Okay. And here is my claim. My claim is this. Now, if I know the internal energy, I will be able to get heat capacity by derivative. Right? So the claim is this. This is the internal energy for the system I want is related to the internal energy of the simpler system, a 1D system, multiplied by 3. Okay, so again, I can live in 1D and then just be careful of the constant multiplier. And if I take derivative, right? What's the derivative? Derivative with respect to temperature. I will get my C, V, 3D. Okay, 3D like this. And this is easy. The 3 you can pull out. So the derivative only see this. 1D. Okay, so now the question is this. From here to here is obvious. So why do we have the first line? So this is when I need your input. So I want a very quick answer sent to me using the chat box, a private message, and tell me why this is the case. Why can I write this down? And this will really test your understanding. If you answer it correctly, this is really a matter of one sentence. So why can I do it like this? Okay. Okay, I get some answer coming in. This is really something that you can have very precise answer. There's no ambiguity. You don't even need to think about the answer. Now, if you give me an answer, I will be able to really quickly tell you this is correct without trying to guess the meaning behind the sentence. So what is the answer? Well, now this bit paper is again begin to get crazy. More. Okay, I begin to get one answer I like. Okay, can I for students writing the E, there are three students like this. Now I want something very mathematical actually. A lot of them are maybe correct. It depends on how you say it. Then you give me one sentence. It depends on your second sentence. So you give me a reason. I will ask you, so what? Then you have to write more. Now let's continue. So the answer is this. The reason you can write this is because of the log. So how do I write down the partition function? How do I write down the relationship between the internal energy and the partition function? You have this log, right? So let me remind you that we are working on the single particle. And now if you apply this equation for this line, you get this line here. Okay, so there are two students who really write down this according to this argument. Okay, the rest about the independent whatever, those are my argument earlier. So those arguments lead to this line, right? Can you hear me? Can you hear me? Okay, somehow something happened with my screen. Wait a minute. Okay, it was interrupted, right? What was the last sentence you heard from me? Can you see the screen? Thank you. Right. All right. So something is something happened with my Wi-Fi, I think. And now I talk about this this part here. Did you hear me or? Okay. Okay. I think you get everything. I think you get everything. I will watch my own video again. Okay. If there's any gap, I will patch it for you. Okay, so don't worry too much. So now basically we know how to justify all this, and now it's the time to really plug in the partition function and get to the heat capacity. Okay. All right. So we are going to do this. And this is messy stuff. Huh? This is coming from here. So let's change color. So this is this line here is single particle partition function. Sorry. Okay, let's begin to calculate U1D. U1D, we have this formula I just wrote. So this is N KB T square. Partial derivative of log of this formula here. Okay, so I have a log. I take log. This becomes two terms, right? So I will have a minus h bar omega and 2 kBT. And then I have this term in the bracket, which I will, because it's in the denominator, I want to write it in this form. So there's a minus sign in front. So this is 1 minus h bar omega kBT. How many brackets? Like this. Okay. And for U1D, what I will get then is I will have now there are two more lines. You can really just take the derivative and rearrange. And I will write down the answer. And there's this. N times h bar omega plus n h bar omega divided by this factor e to the minus, so e to the plus h bar omega kbt minus 1. Okay, so there are a few lines here, so please fill in the gap. Okay, so this is done. And the next thing is you take the derivative again. And that gives you C 1D. If you take the derivative, du 1D dt. And that will give you 0 for the first term. This is a very famous result. We know 0 point energy doesn't contribute to the heat capacity. So for example, in solid state physics textbook, this 0 point energy, because the way the treatment there is a bit different. So this 0 point energy, if you write it down, is very messy. So sometimes many books just ignore this. But here, if you have taken this course, you shouldn't be complaining. Okay, now if you take the first term, really is the 0 point energy contribution, and that doesn't really contribute to the T dependence. There's no T dependence, so the first term is 0. And again, you take the partial derivative for the remaining term. Okay, so this is e to the h bar omega kbt minus 1. Okay, again, I will write down the answer. Okay, so there will be n times kb h bar omega kbt square, and then you have this exponential e to the okay. So that's it. This is the heat capacity you want. And to compare with the experiment, I want this form. I want C 3D. So C 3D. And that is 3 times. So let me use a color to put this 3 here for you. Okay, so this is 3 times. Okay, so this is the form here. And there are more steps here. Now you don't have to do it now, but maybe later you can really plot it out. Okay, so what do you plot? You plot CV, temperature dependent of heat capacity. Then you can verify what I claimed earlier, or what I claimed on Monday. I told you the heat capacity will grow from 0 and it will keep growing, and then it will saturate at high temperature. And it will not plummet. It will not go down to 0. And the physical argument was given to you earlier, and now we do it. We do the very honest treatment, and you should be able to verify my claim. If you don't trust me, this is the result. So I will need this slide. So let me manage this a bit better. So I will copy this. I go to 21, and I will need this one, this final equation here. Actually, I want this one, and then the rest I don't really care. Okay, so I will then get this figure for you. I have plotted it for you, of course. So let's see whether I can just bring it in. This one. Okay, now this is what I claim, but I also plotted it in a slightly different way. It's the way I like. I plot CV divided by 3 NKB. Okay, so this is something you should link to my previous lecture. I like to plot things like this in the ratio of energy scales. Energy scales relevant to the problem. So you can see I have KBT divided by h bar omega. Now, if you pick a solid, now if you know the chemical bond, you fix the oscillator strength, right? This is how you describe this bond, and this bond will be characterized by this omega. You can then fix it, and all the changes in the heat capacity will be dominated by KBT. So that is to say, you fix the energy spectrum, and you go through the same argument as last time. You talk about high energy limit, high temperature limit, low temperature limit, and in this case, you are comparing again with h bar omega. And what is h bar omega? H bar omega, remember, is a spacing between the adjacent energy level, and this is the relevant scale for the problem. Okay, so at the beginning, when you have no energy, that's to say your KBT is much smaller than the spacing between the ladder. It's the same thing, right? So you have tiny energy, what happens? And when you have a lot of energy, thermal energy, KBT is much larger than the energy spacing, what happens? Okay, so that is the problem that is we learn how to analyze, and we learn how to imagine. Okay, so let's gain a bit more here. So first, let me define a few things for you. Now, this is Einstein problem. So for many textbooks, particularly those from solid-state physics, they like to use a symbol E to denote omega. So this is called the Einstein frequency. Okay, so h bar times this frequency is an energy scale. Okay, so h bar omega will be somewhere here, right? This is your h bar omega E. But sometimes you don't really like to think in terms of frequency. This is not too natural for many people. It depends on your field. Okay, if you are doing experiment, let's say you go to the lab and do this kind of experiment, naturally you want to ask what is the this spacing in terms of temperature. And in that case, you can define another thing, which is called Einstein temperature. So Einstein temperature is simply defined. This is a definition. This is you take this energy. This is an energy, and how do you translate to temperature? You divide by kb. Okay, and this tells you this gives you an Einstein temperature, and that is neat for us. Why? Because if you do it this way, this ratio here will just becomes theta E divided by T. And this ratio here will be the same, but it will be the inverse. So if I do it this way, this is equivalent to T divided by theta E. Sorry. This handwriting is terrible. Theta E. Okay, and now you can begin to see something here. Now this is 1. So this is where temperature T, your temperature of your experiment, is roughly the order of the Einstein temperature of your problem. So this is practical. If I want to do experiment and find the saturation, I naturally will ask you, give me your Einstein temperature. If your Einstein temperature is 100 Kelvin, I will go to 300 Kelvin, then I should be able to see the saturation, right? So when they are equal, they are not quite saturating yet, but eventually they will, not too far away from there, right? So as I say, if I know Einstein temperature is 100 Kelvin, so this is practical. In this unit, I know if I go to 300 Kelvin, I have a factor of 3 compared with this. I will be able to observe the saturation. And of course, this is also, you can also think about this way. This is when the thermal energy is comparable to the energy spacing. So this is also the same as h bar omega E is comparable to kBT. And then, you know, things will begin to get interesting. Okay. And this is one thing. The other thing, now I've dealt with the horizontal axis. I want to look at the vertical axis. I plotted in this way for a reason. And I also want you to pay attention that this one really is this expression here. You can verify it yourself. Fire up your Mathematica or whatever plotting software you like. You will see that this will approach 1. So this is when you have the heat capacity to be 3 nkb. Now this region is called the classical region. The saturation part is called the classical region, and there's a name for this. This is a classical Dulong Petit law. Okay. Now, what is Dulong Petit law? This is an observation due to these two scientists. They found something like this. They found, I will write it for you. So Dulong Petit. Now, Dulong Petit found that for simple element at high temperature. Now, for students of this class, you can answer what is the meaning of high temperature. Okay, so at high temperature limit, the molar heat capacity, not just saturate, but they observe something even more profound. So that this limit is 25, around 25 joule per mole per Kelvin. That is why they say this is a law, right? So they're so here you have this saturation, and this saturation gives you this value. Okay, so you might have seen this from other courses or maybe from chemistry. Now I can what I can give you is a table. Sorry, not a table, a histogram. This is something I found from a textbook, another textbook. This is there's a table. I didn't find the table. I didn't copy the table for you, but what you should gain from here is this. This is the number of elements, simple elements. So you pick up the periodic table. Some of them are solid that you can study. Some of them you cannot. For example, if you have oxygen, you don't know how to measure the heat capacity. So for those simple elements in the periodic table, you can find on the data book the heat capacity at room temperature. Okay, so this is the heat capacity. This is most likely a chemistry book, but it doesn't matter. This is CP. That doesn't matter too much. Just take it as the heat capacity has been measured, but these are solid anyway. So the difference between CV and CP are not important. And this is at room temperature. Okay, and you will find that, sorry, I don't want to, at room temperature, this is at room temperature. And this histogram tells you how many of them are taking a particular value between some window, within some window. Okay, so you count how many of them, and this histogram tells you there are a lot of them, which kind of center around here. So this is 20, this is 30, so 25 is here, right? This is 25. Okay, so this is 25 joule per Kelvin per mole, 25 joule per Kelvin per mole. So if you take up the textbook, this is where you see a lot of element. Okay, so a lot of elements has this heat capacity. And now come back to my calculation. And this calculation up here, the one I have done up to this point, think carefully, what assumptions did I put in? I really put in something very simple. What I assume independent oscillator. I did my statistical mechanics, right? All this kind of very logical development, and then I did all this derivation. I get to this point. I did not say anything about the chemistry of my solid. I just say there's something that looks like a solid that I can address all these particles, all these atoms. I know the address of all of them, and I get to this point of 3 nkb, and this 3 nkb here.